All right, class, we're going to get started. Okay, so today we have a little bit of ground to cover. You may have noticed in the calendar, we have two sets of lecture notes today, lecture 5 and lecture 6. You'll see lecture 5 is relatively quick. That's why we'll be doing both in one. Today we're going to be talking about probability density functions, PDFs, and cumulative density functions, CDFs. Lecture 5, or the notes for LO5, are going to be an example of how to compute these things empirically. So we're going to look at that division of air quality data that we cleaned up in pandas a couple lectures ago. And then lecture notes set 6 are discussing some different distributions that we will encounter, and we'll look at analytical descriptions of those distributions for PDF and CDF. I also know that we want to go over, I would like to go over the quiz. I'm not quite done grading it. And so since we have two sets of lecture notes to get through today, we're going to do that on Wednesday. Okay. Any questions before we get started today? Okay. All right. So like I said, we're going to start with looking at probability density functions, and we're going to develop some more ideas about probability density functions based on an empirical data set. So we've already talked a little bit about PDFs, probability density functions, back in lecture 1, but we'll get a little bit more insight into them today. Okay, so we're going to start with this air pollution data that we looked at in the pandas lecture. It was lecture 3. And so just as before, we're using pandas to handle this tabular data. We said it excels at Excel. So we're doing that here. And so we've read in that data. We're displaying the head, so just the first 5 rows of that data just to get a sense. And if you remember, we had all kinds of missing data that was denoted by this negative 9,999 value in this data set. And so we went through this last time, but we can then clean the data. In this case, we're going to clean the data and change the units of time from seconds to days and store that in a new column. And then we reorder them so that that new column is the first one. This is a little bit different than what we had here, but we're going to be essentially going through and replacing all of the invalid values with nans. And then the next lines move the columns around. Once we've done that, we can look at, again, we're going to look at the head and tail of that data set. And we can see that those negative 9,999 values for the UU site have been replaced. We had some others at the Hawthorne site, and we can see that those have been replaced as well. And then again, this is more or less review from last time. We can then plot that data. In this case, we saw that the data from the UU site was missing a huge amount of the time points, something that you'd really only get by plotting the data, which again, we did via pandas. So we then started to discuss how we can plot this data as a histogram in the last lecture, in the lecture on pandas. And so this is showing that again. So we're showing this as a histogram, right? So this from this DEQ data, right, which is our data frame, our pandas data frame. We can use the hist command to create a histogram. Again, I'm hovering over it, and we can see a large number of the different options that we have within pandas for dealing with those. But here I'm just putting an X label and a Y label, and then showing that data, and we get this result here. And now this shows us so this histogram shows us the frequency with which we observed, in this case, PM 2.5 measurements within specified ranges, right? So it's telling us that between 0 and, what is this, about 7.5 microgram per cubic meter, we saw over 1,000 counts of individual data points that fall within that bin, that fall within that time period. And we can read that the same way, going all the way down this curve. This is related to a probability density function, or a PDF, but there's an important property here that's missing. Can anyone maybe point me towards something that's missing here? When we're talking about a probability density function, this came up on the first quiz. So there's a probability density function that this definitely does not satisfy. Yeah. Yeah, so the integral needs to be equal to 1. So for a probability density function, or if we have continuous data, the probability density function, the integral of that probability density function must be equal to 1. And so here, if we were to start, so the integral, we can think of that like a discrete approximation of that integral would be, in this case, just adding up all of the values that we have here. And we can see that we're going to get something that is much, much greater than 1, right? Because this is in terms of frequency, this is in terms of counts, the number of times that we saw those values, and it hasn't been normalized. Right? So this has not been normalized. And so what we can do, right? And so here we're just showing, sorry, before we get to normalization, we're going to look at the UU data set as well with the same thing. And here we're going to see a histogram that in this case appears to be bimodal, likely an artifact of the fact that we have a much shorter, or only have data over a much shorter period of time. But again, this is a histogram plotting frequency versus the ranges of values. We haven't yet normalized this into something that's going to tell us about what the PDF looks like for this function. So if we use this option, so within pandas, right? So now if we're working with real data, we have it loaded into a pandas data frame, we can use this option density equals true, which now turns that data or normalizes that data to give us an approximation of the PDF, the probability density function. That's where that density in here comes from. And what this is going to do is then give us that, right? So remember, our probability density function has this property that, again, the integral is equal to 1, which is definitely not satisfied if we have everything here in terms of counts. But if we then use that density equals true option, then now you can see that the probability density, so we've labeled it as probability density on the y-axis, we have much, much smaller values, right? So instead of having values above 1,000, right, because those were counts, the number of times we actually observed those values, now we're looking at the frequency that we've observed those values normalized by the total number of observations. So put another way, this is now saying this first bin here shows that we have just over 6.5% of the observed values were within this bin. Does that make sense? So that's how we normalize. So, and more or less all that we've done here is just divide by the number of total observations, divide our histogram values by the number of total observations. So now this gives us essentially the density of probabilities within each individual range. It's where that PDF probability density function idea comes from. So this is telling us how likely, empirically, based on the data that we actually observed, this tells us something about how likely we are to get a value, for example, between 22.5 and 30 microgram per cubic meter. Right. This is roughly what we would expect to see if we were to make another measurement. So there we've taken our empirical data and we've plotted an estimate of the PDF from that empirical data. Yep. Yep. Yep, that's correct. That is correct. Yeah, other questions? It is so this is telling us that 6.5% of our observations lied within that bin, is what it's telling us. Yes. Exactly. Yeah. So the majority are in that bin. Oh, you're saying that's. That is correct. Actually, yeah, I apologize. because there's roughly, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, just call it 10 bins. So they would have to be, you're correct, actually. I apologize. You're correct. Yeah, so let's just, let me walk you through this again. So we have the property of our PDF is that the integral of f of x times dx has to be equal to 1. So what our discrete approximation to this would be that the value of our normalized PDF, the sum of the value of our normalized PDF times the bin width has to sum up to 1. Yeah, that's correct. So in this case, the value at that, that 6.5, that 0.065 times the bin width of 7.5, we're going to add that to the value of the next bin width times the bin width itself, and so on all the way up. And that is what sums to 1 in this. So it is not simply normalized by the number of observations. It's also normalized by the width of the bin. That is correct. Yeah. So, yeah. There is a way to define the bin width. I don't know the option offhand in pandas. There is an option to define the bin width or the number of bins, right? So you could also, alternatively, you might specify the number of bins. Yeah. So in data like this, where we have so many measured values, you can likely get a very nice smooth histogram with thinner bins than the default in this case. Looks like it was 10. Yeah. Good question. Okay, sorry. Thank you for the catch. Other questions on that? Okay. But this has now given us an estimate of the PDF that is now normalized by the number of observations and the bin width. So we can take this same data and we can now normalize it by the we can now look at the cumulative density function, which tells us the probability that we have, the cumulative probability that we have values up to a specified, in this case, a specified PM 2.5 reading. And you can see actually the way that was computed. In this case, we have many more bins. So here's actually the answer to your question about can we set the number of bins is actually right in the next line of code. So here we're setting not the bin width, we're setting the number of bins. In this case equal to 45. So you can see we have much smaller bins, right? Much smaller width bins here. And when we do that, and in this case, then what we're doing is using this cumulative equals true. So we're using density equals true in order to tell us indicate that we're using the PDF rather than the frequency, right? Rather than the absolute frequency of the observations. And we're using this option of plotting, instead of the probability density function, we're plotting the cumulative density function. All right, so we've normalized by the bin width using this density option and number of observations. And then we're plotting the cumulative or the sum of all observations within these ranges using the cumulative option. And when we do this, we get this CDF or cumulative density function, which tells us we can interpret this as telling us the relative frequency that we're going to see a value between 0 and whatever the specified value is on the x-axis. So let's start all the way out here. Right, what it's telling us is that we expect to see 100%, right? We expect to see all of our results between 0 and 70 microgram per cubic meter. And similarly, it gives us the probability then of seeing a result between 0 and 20 microgram per cubic meter. We can read off here as something around 0.75. Right. So we'll see that we're going to be using this cumulative density function in order to tell us about, for example, when we know what the distribution is, either in this case empirically or based on an analytical solution to what the PDF or CDF is, we can use this to find the probability that we have any specified range of results in our output. All right, so I said, so we can find the probability that we have something between 0 and 20, right, would be that roughly 0.75. But now if I ask you, what's the probability we have something between 20 and 70? And we can find that by taking the probability from 0 to 70 and then subtracting the probability from 0 to 20. All right, so we can use this to find probability of getting a result within any specified range. That's really what we use the CDF for. Yeah. Can we only do this in Python with histograms? So the question is, can we only do this in Python with histograms? So in this case, we have data, right? So we have actual measurements from a continuous random variable, right, which is this PM2.5. We have the measurements that we've made. And so when we're looking at those measurements, if we don't know what the exact shape of this thing is, then we can't really plot a continuous curve, right? We could refine the bin widths and make smaller and smaller bins, make something that more closely approximates a continuous curve. But we're always limited by the fact that we have a finite sample, right? The next piece of this, LO6, is where we're going to look at cases where we know what the PDF is. Like we know what the shape is analytically, and then we can plot a perfectly smooth continuous curve, okay? So in cases where you know that, or you fit your data to that curve, right, then we can use the methods from LO6, okay? Yeah. All right, good question. Any other questions about this so far? Okay, so we're going to see, and especially when we get into LO6, we're going to look at examples of how we can use PDFs and CDFs to solve problems. We're going to see that the CDF is actually going to be a really useful tool for defining probabilities or probabilities of seeing things within certain ranges. We're going to generally use the CDF. So we can also, again, we can look at the median and the average concentrations using pandas, which, again, I believe we showed last time. But one thing to note here is that the median and the mean, these are both measurements of sort of where the middle of the data set is, right? The mean is just the sum of all the values divided by the number of observations, and the median is the middle observation. So if we take all of our observations, like on problem 3 on the exam, take all of those observations and put them out in order, which one happens right in the middle? And for a symmetric distribution, the mean and the median should be about the same, or it should be exactly the same if we have an analytical solution, but if we have real data, we should expect them to be about the same. In this case, the values are very different, 7.7 and 13, indicating that we have a skewed distribution, indicating that the distribution is not symmetric. And that is, in fact, the case, right? If we look at our distribution, we can see that it is definitely not symmetric, right? It tails out to one side. We'll look more at measures of distributions as we move on in future lectures, but for now, just know that one way of determining that we have kind of a skewed distribution is by seeing that the mean and the median are different. So another example, when we were introducing the idea of mean and median, was like salary data, right? If you look at salary data, those tend to be highly skewed, right? With some people making a lot more money than everyone else. And so the mean and the median are typically not the same in salary data either. And again, the interpretation of the median says that half of the values are above it, half of it are below it. In this case, we have empirical data on PM2.5. And so the median of 7.74 microgram per cubic meter means that half of our observations were below 7.74, half of our observations were above. All right, so we can then also look at these CDFs or cumulative distribution functions for some of our different sites individually using pandas. And again, one of the nice things about using pandas is that our data is labeled by the site, and we can, instead of having, again, to remember like exactly which column corresponded to which site or which piece of the data corresponded to which site, we can just call them out by name, and pandas will present the data for us. Okay, so this was a very brief introduction to PDF and CDF using this data set that we'd already looked at previously. Next, we're going to go and look at some additional analytical forms of PDFs and CDFs that arise when we have different kinds of processes occurring. We're going to revisit binomial, for example. Partway through the next set of lecture notes, we're going to revisit the binomial distribution. But any questions on this so far? Okay. So this, again, was an example when we have real data. In this case, we didn't exactly know an analytical form of the PDF or CDF because we don't really know that many yet. We've really just talked about the PMF for binomial. That's as far as we've gotten. But so we can build up, we're going to start to build up a library of different kinds of distributions that we might see. So again, we're on LO6 notes now. Just a note on Canvas, you may notice, I think the lecture notes folder was getting a little bit crowded. And so I started by creating a subfolder just for the lecture notes that we were going to do today that has all the data files and everything that we need for the lecture. I think I'm going to continue that moving forward. And I might clean up the old lecture notes as well one of these days. So if things are in slightly different places than you saw before, that's where they went. If you want to know which lecture notes, because the number of what lecture note we're on doesn't exactly correspond to anything, but it does correspond to the information that's in the calendar. So if you want to know which lecture notes you need for a given class period, then check the calendar, which is on Canvas, on the main page of Canvas at the bottom. Also has suggested reading assignments. Okay. So now we're going to look at some analytical solutions. One note here is this statement here: analytic distributions can be used to model empirical distributions. And then one reason why we might want to do this is that then we can do things like, then we have continuous data that we can, or a continuous distribution that we can use to make estimates over any range that we would like. And it's saying two common applications would be interpolation, so filling in for data that we maybe haven't measured yet, and calculation of confidence intervals, which is going to bring us back to this idea of what the CDF is. And then just a note, again, sort of review from previous material. We looked at, in lecture 1, for example, we looked at the binomial distribution, and we defined the probability mass function called PMF. And we said it's basically like the PDF, but for a discrete variable. So PDF is, again, for variables that can take on continuous values. So PM 2.5 could be, essentially any continuous value, right? We can measure it out to however many decimal places we would like. Height is something, right, that has a continuous value, right? We can measure height to whatever precision we'd like. And then PMF is for discrete events. So for example, when we're talking about cancer cases on a block, you either were diagnosed with cancer in the past year or you were not, right? So that was either a 1 or a 0. And so there we talk about a PMF, probability mass function, instead of a PDF. You look like I could help you. The PMF 2.5. Oh, PM 2.5. Sorry. PM 2.5 would be example. So measurements of PM 2.5 would be examples of a, or we would analyze that as a PDF, or a probability density function, because it's a continuous variable. Yeah. Apologies if I said PMF 2.5. There's a chance. Okay. And so we're going to look at, in this lecture 6 notes, we're going to look at 2 examples of PDFs and 2 examples of PMFs. So the first example is going to be the exponential distribution. And one thing that we're going to see in this discussion is that these different distributions essentially model the probability of events that have different features. And so one of the maybe key places where you might get mixed up on this, And so something to pay attention to is essentially knowing when, under what conditions these different distributions apply. So thinking ahead to a future quiz, I'm going to give you the PDFs and CDFs that we're going to discuss today, right? Those equations will be on your equation sheet. But I'll still expect you to know when to apply exponential, the exponential distribution. We're going to talk about normal distribution, when to apply a normal distribution. You'll have binomial again, right? When should you apply that? So one of the key things here is knowing, under what conditions do these types of distributions hold? Okay, and then the rest of it will be going through the math to figure out what the PDF and CDF, in this case, we're just defining what the PDF and CDF are, and we'll look at the results of some of the mathematics, looking at mean and other properties of these things. But one of the key things to pay attention to here is just like what kinds of processes do these distributions describe? Okay. So the exponential distribution is where we're starting. We can think of this as the probability distribution for the time between events that occur at a constant average rate. So if we have a number of events that are happening and we're looking at just the time between them, we'll see an example of this once we've defined the properties of this exponential function. But it might be the time between arrivals of people to a store, right? Or the time between failures of a particular process, right? Chemical process that we're running, something, right? If we have such a process where we're concerned with the time between events, the time between those events will follow, if those events are occurring at a constant average rate, then the time between those events will follow the exponential distribution. And so, and we're going to define that constant average rate as 1 over lambda. Is going to be the rate at which we have the events occurring, right? So it'd be like the average rate of people arriving in line. The average rate of failures occurring would be 1 over lambda. Yeah.
What's lambda?
So lambda would be in units of time, because then rate is 1 over time. Yeah. So for example, it could be in seconds and hertz, right? Lambda could be in seconds and the rate could be in hertz. Lambda would be like the average. Yeah. So lambda would be like the average time between events, right? So the average time between people arriving in line, average time between failure events occurring. Yeah. So for such a process where, again, our random variable here, x, is the time between events that are occurring, then the PDF is defined as lambda times the exponential of minus lambda x. And then the integral of this gives us the CDF. And the CDF is just 1 minus exponential of minus lambda x. So probability density function and cumulative density function are shown here. And we can plot these. Okay. And these are plotted. So this is the CDF now is plotted down below, or in this section here for different values of lambda. I'm just going to go back up in our notes. So the other important properties of this exponential distribution to know, other than when it applies, are the mean, medians, and variance. So the mean is possibly the most important one to know. This is just 1 over lambda. So it's telling us, again, more or less what we would expect, what we defined up here, right? We said that the average rate was 1 over lambda. And this is telling us that if we take this PDF and we compute the mean of this PDF, we recover 1 over lambda. Okay. The median is log of 2 over lambda, and the variance is 1 over lambda squared. And then because this, so again, we'll note that the median and the mean are not equal to one another, which tells us that we have some degree of skew, right? From knowing that those two things are different from one another tells us that it's asymmetric, right? So we don't have a symmetric distribution. So these two things are not going to be equal to one another. And when we plot it down below, we'll see that that is in fact the case. As an example here, mean and median of an exponential distribution. So we're going to calculate mean and median for an exponential distribution with lambda is equal to 2. Knowing that log of 2 is 0.693, or we can compute log of 2. Natural log of 2 is 0.693. So lambda is 2. The mean then of that distribution would be 1 over lambda. And the median would be log 2, right? Natural log of 2 divided by lambda. And so we have those results down here. So the mean is 0.5 and the median is 0.35. So now we're going to plot the CDF for a range of these different exponential distributions. Just double check that we have the PDF. We do have a PDF plot next. We are using the exponential. We're just using the definition of the CDF that we wrote up above and the exponential function in NumPy. And we can see that we have, and we're creating arrays that now have the data in there for 3 different values of lambda, in this case 0.5, 1, and 2, and then plotting those below. And so when we do that, right, we have this nice plot showing us the exponential distribution for 3 different values of lambda. So what this is showing us is that if the as we end up with faster and faster rate, we end up shifting this distribution back towards shorter and shorter time intervals. So as we have a faster rate, then we end up with more events occurring with shorter time intervals. And we'll see that when we look at the PDF as well. So again, here we're defining, we're going to plot the PDF for the exponential distribution just by plugging in the definition of what the exponential distribution PDF looks like, right? As lambda times the exponential of minus lambda times x. We're using the same range of x values that we had previously. And this is what we see for the distribution of the exponential, our exponential distribution PDFs. And again, it's showing us that if we have events occurring at a faster rate, higher lambda, then we have typically a shorter time between those events. Okay, yeah.
Is the x-axis here, is that units of time, or is that like number?
Yeah, x-axis is units of time. Yes, in this case, x-axis is units of time. Yep, that's correct. So if we think of the PDF is the integral of the CDF, then we can reverse that, and we could also say that the derivative of a CDF is a PDF. And we can find the and we can therefore convert back and forth between PDF and CDF, right? We can go either way. So one example of applications for this, just to preview something we're going to talk about later. So in later lecture, in this case, lecture 25, but in later lectures, we're going to look at more applications of the concepts that we're covering now in different processes in chemical engineering. And so, for example, we'll derive that PDF for this time, residence time within this ideal continuously stirred tank reactor. And we'll see that we're going to have this PDF following the exponential distribution. But here's another example, a more concrete example that we're prepared for now. And so this is, imagine we have some kind of a nuclear reaction occurring, and we want to know the time, or what and our data is going to be the time between emissions. right? So if we have emissions of some kind of radiation particle, in this case, beta particle, and we want to know that, we want to know what is the distribution of times between these emission events. And so with this exponential distribution, if we expect that it follows an exponential distribution, we just need to know the average rate, right? This 1 over lambda, and then we can start plotting, for example, the PDF and the CDF. And so what in this case, what we've done here is read in the actual data on emissions of these particles, of these beta particles. So it's stored in this file, beta emissions .csv. And I believe I have the header is down here, right? So it's really just a list of the time between measured particle emission events, right? So that's our data. So imagine we have a counter sitting there counting when beta particles, we have an indicator there sitting there that indicates when a beta particle is emitted. And what our data is, imagine you're sitting there with a stopwatch or something, just recording the time between when those particle events occurred. And then you're putting that down into a big list, right? That's what our data is. So we might expect that this kind of data follows a exponential distribution. And so here, more or less, we're going to investigate whether or not this data is well fit by an exponential distribution. And so given that we know that the exponential distribution really only depends on the mean or the average time between events, we're just going to take this list of event times and find the average time between events. Right? In this case, it's 0.55 seconds is the average time between beta particle events. And now with that, we can plot what the PDF would be for an exponential distribution with a mean time between events of 0.55. And when we know everything that we need to, we know a lot of different properties of our distribution. We know the distribution shape, we know the different values of that distribution based on just that mean time between events. So in this case, so lambda is going to be 1 over that mean time. Sorry, that time is in milliseconds, not in seconds. We have our average is 0.55 and our median is 0.294. Is what we would expect for, again, an exponential process with a mean time between events of 0.549 milliseconds. We can actually go ahead and compare. So this is what we would expect for theoretical distribution. We can actually compare it to what we actually see. And we see that for the actual data, we have 0.2945 as the median, which is pretty close to what we're going to expect, actually almost bang on with what we would expect just by using the definition of the exponential distribution. But we're going to go a little bit further and plot it. So in this case, we're creating a variable against which we're going to plot our PDF for an exponential distribution. So again, we're just defining it using the definition of what the exponential distribution is. Using lambda that's based on the observed average value. And then here we're going to plot that on top of a histogram, which is normalized. So here we're using density equal to 1 as an alternative to density equals true. So we're going to plot an approximation to the PDF from the actual data alongside our theoretical curve for what the what the exponential distribution looks like. And when we plot the two together, we see that the data shown as the histogram in blue corresponds pretty well to what we would expect for an exponential process. Okay. So what this is telling us is that the exponential distribution appears to describe the data pretty well. These two things match pretty well. Does that make sense? So again, we loaded in this data that we had on time between events. One question we might have is, does this follow an exponential distribution? Does the time between events follow an exponential distribution? We know that exponential distribution only depends on the mean time between events. So we just took that big long list of time between events, computed the mean, and from that we can get an expression for what we expect the exponential distribution to look like. We've plotted that in red, and we see that it pretty closely matches what we actually observed in that blue data set. Okay. So to make a better statistical determination of whether or not this follows the exponential distribution, we'd have to go a little bit further into curve fitting, which again is something we're going to cover a bit more later. But from the outset, I would say this seems to work pretty well. Okay. Any questions on that, on exponential distribution? Yeah.
Just like this.
Yeah. So it's telling us that we expect to see sorry. Hold on 1 second. Just run it all. It's telling us that we expect to see most of our events, for example, between that 0 and 0.4 milliseconds. Sorry, is there something here that doesn't look quite right? Is there something about this plot that doesn't look quite right? Yeah. It would appear to integrate to a value greater than 1. That's correct. Because we can see that this, no, this plot does not integrate to a value greater than 1. Because when we multiply by the bin width, we're going to end up with a cumulative value, which is less than 1. That's correct. Yeah. Sorry. So one way to interpret this would be as the relative frequency of seeing events, for example, within these different bins, right? So it's telling us, for example, that we are, so this was, let's say it's about 0.3 and this is about 1.5. So we're saying we're about, maybe 5-fold more likely to see events happening at, within this bin than we are within this bin, right? So if we were to look at the CDF instead, the cumulative density function instead, then we can more directly interpret the values at different intervals as telling us the probability of seeing events of those specified durations, if that makes sense. But yeah, in this case, we can interpret it, say, to tell us about relative frequencies between events. Yeah. Okay. Other questions about exponential? Okay. So, but again, one key thing to take away is that when we are looking at the time between events, right, when our data is about time between events that have constant, and we have a constant average time between events, we can use this exponential distribution. Okay, so the next one is the normal distribution. Normal distribution is something that pops up all over the place. So in general, if we have data that are affected by many small, unrelated, and random events, then what we end up with is the normal distribution. And there's some kind of elegant mathematics behind why we expect to see a normal distribution, and I will at least link to a video discussing some of that if you're interested. Because the places where it comes from is actually kind of interesting math. But the end result of it is that the normal distribution is something that we see all the time in real data. So the things for you to know here is just that, when we have many small unrelated random events, then the distribution that we tend to see is the normal distribution. So, it's some of the many examples in which we see the normal distribution. You look at people's weights and heights. We look at average temperatures, fluctuations in the stock market, even often grades within distribution of grades within a class on a certain exam, right, or overall average grades within the class, all of this tends to follow something like the normal distribution, because we can think of each of these different processes, even though they're totally unrelated to one another, as being influenced by many, many small unrelated sort of random events. So when that's true, and again, it's often true, or it's often at least approximately true. So normal distribution is one of the most useful distributions that we'll see in statistics. Then we can describe the PDF, or the probability density function, as f of x, right, where x is the value, the random variable that we're trying to describe. It's also going to be a function of mu, which is the mean, and sigma, which is the standard deviation of the data. And then we write it out in this way: 1 over square root of 2 pi sigma exponential minus x minus mu squared over 2 sigma squared. Right, so in contrast to the exponential distribution, we started with that because there's only one parameter, right, that mean time between events. Here we have two parameters: the average value of our observations, and the average value that we expect to observe, which is mu, and the standard deviation sigma, or the variance sigma squared. So it depends on just those two parameters, the mean and variance, or mean and standard deviation, which would be the square root of the variance. And one thing that we'll often do when defining the normal distribution is we'll take our values, right, our observed values or our measured values, the mean and the standard deviation, and combine them into something called the z-score. And this lets us just write out a simpler form of the normal distribution. So if we define z is x minus mu over sigma, we can think of z-score as telling us something like a normalized value of how far away something is from the mean, right? So if something is, if a say a measured value has a really high z-score relative to let's say the standard deviation and the mean of a data set, that's telling us that it is really far away from the mean relative to the shape of the normal distribution. So we can use it, we'll use this often when we're talking about normally distributed data. But if we define a z-score in this way, then we can simplify our PDF as PDF of z is just 1 over square root of 2 pi exponential minus z squared over 2. And then in terms of that PDF and z-score, we can then write out the cumulative density function for this normal distribution as the integral of that function. Yeah. Yeah, that got... I need to track that down and make sure that there's not an error in the notes, and or be able to show you where that came from. But I don't have that right now. I will follow up on that either on Canvas or next time in lecture. Okay. And if I don't, remind me and I'll keep trying. Yeah, that's a good question. Yeah, so the question is, where did the sigma go between 5 and 7? And my answer for now is I'll get back to you on that. Yeah. So anyway, in terms of z-scores, so if we keep our definition in terms of z-scores, we can write out the CDF as follows, essentially as the integral of this expression. And this is the integral from minus infinity to whatever our specified z-score is, right? So again, cumulative density function tells us the probability of having a result between, in this case, negative infinity and whatever specified value that we're looking at. So this is the definition of that. I give this one as well. I guess I should have an equation number here. In terms of the error function, can just be a little bit more convenient. Error function is defined on some calculators, so this is a useful one to have as well. Without getting into what the error function is, that can be a useful thing to have, and will be on your equation sheet. But with this definition of the CDF, or cumulative density function, for the normal distribution, we can start to look at some of the properties. So some special values. For example, if we have a CDF of 0, so if we have the normal distribution and we look at the CDF of 0, if we follow through with either of these expressions and compute that, what we end up with is that CDF of 0 is equal to 0.5. So what this is telling us is that the distribution is symmetric about this point 0, or around a value of 0. So the normal distribution defined in terms of z-scores is symmetric about 0, meaning 50% of the values are below 0 and 50% of the values are above 0. We can look at CDF. So again, remember the cumulative density function, the CDF, tells us the probability that we have a value between, in this case, negative infinity and whatever value of z-score we're looking at. So that means we can find the probability of getting an event within a specified range as the difference in those CDF or computed CDFs. And so in this case, if we look at CDF of 1, so CDF for a z-score of 1, and subtract from it the CDF of a z-score of -1, then we end up with 0.683, again, telling us that 68.3 of z-scores are within plus or minus 1 standard deviation of the mean. So this came up in lecture 1. We said we had some data. We said we computed what the standard deviation was, and we just kind of said, take my word for it, that this tells us that roughly 68% of the data lies within that 1 standard deviation of the mean. That comes from assuming that the data is normally distributed. So if we have normally distributed data, then we know that that we're going to see roughly 68% of the data within 1 standard deviation of the mean. We can do the same thing for 2 standard deviations of the mean, and we get a value of 0.954, showing us that 95.4% of the data, about 95% of the data, are within 2 standard deviations of the mean. And these are the actual computed CDF values using this stats.norm function, stats.norm.cdf function. We're then plotting the CDF values for these different values of z-score. And what we would see is that if we have if we take this value minus this value is what we're computing down here, we end up with that 68.3%. This is telling us 68.3% of the data is within 1 standard deviation of the mean. And if we look at this value minus this value, that gives us the fraction of results that are within 2 standard deviations of the mean, and it works out to 0.954. We can just another definition here is the percent point function. So percent point function is inverse of CDF. So if you know the fraction of data between, in this case, negative infinity and a specified value, you can invert that using this PPF. And so here we're just inverting that using the values that we got from the normal distribution CDF and recovering our original z-scores. Let's look at a plot here. This will be a little bit, I think, more informative. So we're plotting the CDF for a normal distribution over -4 to 4 over z-scores of -4 to 4. And when we do that, we get this result. So this is the CDF, cumulative density function, that is showing for a normal distribution over values that are 4 standard deviations away from the mean, to value in negative direction to values that are 4 standard deviations away from the mean in the positive direction. So again, if we wanted to know, for example, the number of values that we would expect to see within, or the probability that we expect to see an event within -1 to 1 standard deviation, -1 to 0 standard deviations of the mean, that would be the CDF from CDF of -1 subtracted from the CDF at 0 would give us the area between this curve, tells us about the probability of an event between these two specified z values. Does that make sense? I feel like I'm not explaining that great. So anyone, so what does the area under this curve represent? Can someone tell me what the area under this curve represents? Yeah.
Any point.
The probability of a value, the probability of value is lower than that point. It's between negative infinity and that number. So the CDF of 0 tells us that we have is 0.5, and that tells us that we have a 50% chance of getting, when we have normally distributed data, we have a 50% chance of getting a value between -infinity and 0, or a z-score between -infinity and 0. That's correct. And so based on that, we can then we know that the total integral, right? The CDF of positive infinity is going to be just 1, right? So that tells us that the we can then say that the probability of seeing an event between 0 and positive infinity is just 1 minus the CDF of 0, or 1 minus 0.5. That's also 0.5. That makes sense. And so we can use this then to find the probability of events within a specified range of values. Yeah.
So, and because of what the z-score means, that 50% of the data that's normally distributed is greater than the mean.
That's correct. Yep. So again, so z-score represents, right? Z-score is the random variable x minus the mean divided by standard deviation. So think of it as like a normalized measure of how far a value is away from the mean. And so this thing, if our x value is equal to the mean, then our z-score is 0, right? Because the x value then minus the mean would be 0. And then, so this is telling us that 50% for normally distributed data, 50% of the values are less than the mean. That's it. Yeah. Okay. And then this is, if we look at the PDF of the normal distribution, this is what we see, right? This is the typical bell curve that we think of as describing normally distributed data. Okay. And again, the integral of this gives us a CDF from which we can compute probabilities over different intervals. Okay. So the next bit here is showing us how we can essentially show the or color these different distributions and fill, right? So we're using this fill between function to now color in different regions, right, representing these different areas underneath the curve. In this case, we're showing the area underneath the PDF between -2 and 2. So another way to think of this is the area, or this area underneath this curve represents the shaded area here represents the probability that we have an event between -2 and 2 z-score. And so this should work out to being about 95% of the total area under the curve is now shaded here in blue. Here we're just showing that we can also plot lines. So here's code to plot lines at -2 and 2 and overlay them on this function. So then what we've described here is the PDF and CDF for a normal distribution in terms of z-score. So we can think of it as like a generic normal distribution, right? We've described the normal distribution in terms of how far we are from the mean normalized by the standard deviation. But if we have a real process, we don't often have a mean of 0 and a standard deviation of 1. So what we generally are going to have to do is then scale the PDF based on our actual mean and standard deviation. Right? So actually, we can go kind of two ways. So one way, we can just take all of our values and put them into z-scores and use the expressions that we had before. Or we can take our expression for the normal distribution, PDF and CDF, and rewrite them based on the, or shift them based on the actual mean and standard deviation. And so here we're doing that for a mean of -1 and a standard deviation of 1.5, or a mean of 2 and a standard deviation of 0.5. And we can see that we're plotting them down below here and showing what those different normal distributions look like. All right, so we've basically just taken that same normalized distribution, or sorry, normal distribution that was based on a z-score, and we've just shifted it left or right based on the mean, and scaled it based on the standard deviation, right? And then we get these curves, which might describe, I don't know, say 2 different random variables, right? The distributions that we see for 2 different random variables. That makes sense? Okay. And then again, we have the probability that a value is within any given interval is going to be the CDF. The difference between the CDFs at those values is something we've, I guess, said graphically, but now we're writing it out explicitly. And so here, in terms of z-scores, we have that defined for example, between, again, -1 and 1 z-score, we get that 68.2%. For greater than 2, we have 0.0228, and so on. Okay, so to make it a little more concrete, let's talk about an example just briefly. So if we have weights of a sample of people distributed normally, and we know the mean and the standard deviation. So mean is 140, standard deviation is 25, and we want to know the probability of having someone that weighs, or picking someone out that weighs less than 130 pounds. So what we're going to do is we're going to first compute a z-score for the event that we're trying to analyze. In this case, that event is going to be for someone weighing less than 130 pounds. And so our z-score is 130 minus the mean, 140, over 25. And so our z-score is minus 0.4, right? So it's negative. What does negative mean? Why is it negative? Yeah. Because it's less than the mean, right? So it's negative because the value that we're looking at here is less than the mean, right? And then it's been scaled by the standard deviation. So we have this value of negative 0.4. So another way of saying this is that it is 0.4 of a standard deviation lower than the mean. That's a way of thinking of what the z-score is. And then we wanted the probability that we pick someone out that weighs less than 130 pounds, right? So that's just going to be the CDF at 130, right? The CDF at that specified z-score of minus 0.4, right? Because again, the CDF tells us the probability that we have something lower than the specified number. So in this case, we just find, we're using stats.norm.cdf of our computed z value. And the CDF of minus 0.4 is then this 0.34, right? So it's telling us that for a population with a normal distribution, a mean of 140, and a standard deviation of 25 pounds, then the probability of picking someone out that weighs less than 130 is going to be about 34%. Okay. I'll get some practice on the homework. Any questions on this? Okay. This is showing an example using a calculator. And with the sequence of functions that you can press in on a particular calculator is TI-36X Pro. You can actually do this. So I'd say as we go into, so knowing that we're going to have quizzes where you're using your calculator, look into, for your specific calculator, how to do these different kinds of calculations, okay? So that's one reason why I'm trying to give you the error function. We also have it defined in terms of an interval, which can be done on many calculators. But that's something to look into. So here's an example for one particular TI. Okay. Okay. I think for today, we're going to review binomial and we're going to talk about the Poisson distribution at the beginning of class on Wednesday. So we're going to pick up on the rest of LO6 on Wednesday. So the remainder of today is going to be review of binomial distribution in terms of essentially what we know now or what we've just discussed about PDFs and CDFs. We are starting to run out of time in class and it is starting to run really long, I think. This is a long class period to be continually lecturing, or for you to be sitting through a continual lecture. But so just as a reminder, we already encountered binomial distribution. And again, this is a discrete distribution. And so the discrete analog to a PDF, we call a PMF or probability mass function. And we discussed in those lecture 1 notes that the PMF of K or for our binomial distribution is given as this: n choose K times probability of a given event that we're looking at to the K times 1 minus P to the n minus K. Where this n choose K is, we call it the binomial coefficient, and it's written in terms of these factorials, right? So again, n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So for the binomial distribution, just as a review, we said that the mean was n times p, right? The number of the total number of events times the probability of getting a success on at any given event, n times p. And we said the variance was np times 1 minus p, meaning the standard deviation is the square root of this. And so as a reminder, this describes a random process with just 2 possible outcomes, where we typically call one a success and one a failure. So in the cancer cluster example, we actually called finding a cancer or someone being diagnosed with cancer within a given year. In that case was defined as success, meaning the probability was P. But that's a nomenclature that we typically use when we're talking about binomial. So here's just another example, something that we've seen in homework and in exam. So we have diaper manufacturing, and we know that 1% of the diapers are defective. So if we're selling a package containing 50 diapers, what's the probability of finding 1 defective diaper in a package? So our n is 50, right? Because we're going to have 50 events. The probability of finding a defect, which we're defining as success here, is 0.01. And the number of events that we're looking for is K. It's just equal to 1. And so we're using this binomial PMF based on our K, our N, and our P. And our probability defective is that 0.3. It's about 0.3. We can then compute the mean, the variance, and the skewness, which tells us something about how asymmetric the data set is. And we see that our mean, if we look at this is just going to be n times p, right? Our 50 times 0.01 is going to give us 0.5. Our variance, again, we could find it as np times 1 minus p. We end up with 0.495. And it's telling us that it is skewed. So this value is not 0. And we can plot the distribution, so the PMF now for the binomial distribution, as shown down here. And so this is telling us the probability of getting a certain number of defective diapers within a set of 50 versus the number of defects. And it's showing us what that looks like. And again, we looked at this previously, but now we understand a little bit more about what a PMF is, right, in relation to the PDF. And one thing to note here is that as we get to events where we have n times p or n times 1 minus p, n times 1 minus p, both larger than about 10. So if we have a large number of events and a relatively high frequency with which they occur, this curve actually starts to look more and more like a normal distribution. And so as we have more and more events, we can actually use that normal distribution to approximate the binomial distribution. So again, the normal distribution comes up in many different places. All right, I think we're not going to introduce a new distribution today. There's not enough time left and not enough energy left, I think, either. So we're going to pick up with this, and then we're going to move into lecture note 7 on Wednesday. Any questions or anything before we break? Okay. All right. Thank you all.